All right, ladies and gentlemen, this class recording has started. So, yesterday we talked about the idea that as current flows through a conductor, it creates its own magnetic field. And it can then affect other magnetic objects, right? Remember the field being an area around an object where it can affect other things, right? And that as current flows through that wire, it creates its own magnetic field. It can affect other objects. And we talked about that if we take that conductor and wrap it into a loop, then we can... straw's not connected, so... so that's not gonna sound good on the recording, but whatever. So
I just realized that.
Mora's knocking it out of the park today. This is like the Mora comedy hour today. So all right. We really need video to go along with this class recording. So all right. So we talked about the idea that current causes its own magnetic field. If we take that conductor, wrap it into a loop, the way the field lines up, we turn it into basically like a bar magnet, and that if we continue to make more and more loops, the field gets stronger. We can make a strong magnet that's an electromagnet because it only applies when the electricity is flowing. But what we find out is that also works in reverse. So up on the board, you don't have this picture in your outline, but down here, the little red and black thing here, this is a solenoid. All it is a wire just wrapped around this tube many, many times to create a coil. Okay? The tube is just made of wood. It's not a conductor, right? But it just has a wire that's wrapped around it. It's connected to these two screws that are right here, and we've connected that to an ammeter. This measures current, and we talked yesterday that you can use the solenoid to measure current and stuff like that, but it measures current. There is no battery, there is no voltage source that is connected to this wire. Therefore, there is no current. So you can kind of see in the picture, it's not the clearest picture in the world, but there is no current, that the needle is at 0. But what we can do is we can take a magnet. So this is a bar magnet, and it has its own magnetic field. And if we take that bar magnet and move it, we will see for a very short time the ammeter that measures current jump. And if we move it again, we'll see it jump again. That the movement of the bar magnet is actually causing current to flow through the conductor even though there is no voltage source. So what we find out is that we can produce an electric current by a changing magnetic field. So what we see is that this magnet, as we move it in and out of the coil, just take rapidly and go back, forth, back, forth, back, forth, inside the coil, out of the coil, into the coil, out of the coil, what we find is that this current jumps and it spikes for a short little while and then it goes back. And then jumps again and it goes back, jumps again and goes back. Because it only applies while the magnet moves. If we take the magnet and just set it inside of the coil and just let it lay there, no current. It's only produced by a changing magnetic field. So there has to be some kind of change in the arrangement of the charges or the magnet to cause the current to flow. We call this idea electromagnetic induction, and it was discovered by Faraday, Michael Faraday, who we introduced earlier in this unit. We talked about field theory. So we refer to this idea as Faraday's law, that current can be produced by a changing magnetic field. First, why is it a law? Andrew?
Because it states a fact.
It states a fact, but it doesn't do what? It doesn't explain that fact, right? Okay, so at the time, all we knew was that we could create this current from the changing magnetic field, but not why. Now we've started to figure it out and why it goes with it. Okay. Any changing magnetic field can produce a current. So in the first picture, we took the magnet and moved it in and out of the wire. Here, if we take the wire and move it in and out of the magnet, it can also produce current. So we can produce current by moving the magnet, but we can also produce current by moving the wire and keeping the magnet still. Right? Same idea. As that loop moves in and out of a magnetic field, a current is produced, or we say a current is induced, right? That means we made it happen in the conductor. So as the wire moves, either the wire moves in the magnetic field or the magnetic field moves around the wire. Either one of those things will cause a current. So a current can be produced by rotating the circuit. So we can take this field, this little loop of wire that we've created, and just sort of flip it around back and forth, or move it side to side, spin it in a circle. Any one of those things will produce a current. Or we can leave the loop of wire still and move the magnets around it. Either way, we produce a current, and we call that electromagnetic induction. Okay. Good there. All right. What we find out, though, is that only movement in a certain direction will cause current. A current is only produced when a conductor moves perpendicular to the magnetic field. Current is only produced when a conductor moves perpendicular to the magnetic field. So just because the wire is moving or the magnets are moving doesn't necessarily mean that we're going to produce current. Okay? So, just as a demonstration, all right? Omar, you want to help me out with this? Sure. Stand up for me, please. And grab the other end of this. All right, so here's our conductor, right? This is just a wire. No voltage source. It's not hooked up to a battery, right? I'm not one side of the battery. Omar's on the other side of the battery. It's just the conductor, okay? But if we turn this room into a giant magnet field, okay? North pole is up on the board. South pole is in the cabinets in the back, right? A giant magnetic field, right? If we move this conductor, we can cause current to start flowing through it, right? But we have to move it perpendicular to the field. Hopefully you remember, maybe you don't, but remember we draw arrows to represent the field, right? The direction of the field and how it goes. In a magnetic field, the arrows always go from the North Pole to the South Pole. So if this is a North Pole from one magnet, let's say, and the cabinets are a South Pole from another magnet, the field, the arrows, we would draw from here pointing that way, because it goes from north to south. So it's a bunch of lines that just run from here to there. Okay? We're going to take this, let's hold it up here, right? So if we move it this way, right, or we're just going to move it this way like this, okay, you can go there, right, like this, okay, just like this, okay, alright, hey, quit messing the demonstration. Oh, okay.
Should I show with it?
Go.
That's on recording.
Luckily I said no.
Yeah.
Alright, as Omar and I move in this direction, right, or if we move back in this direction, okay, actually I should move you down this way so get you away from Trey so he's not messing up the demonstration, okay, alright. We are moving in a direction that is parallel with the field, right? The lines are going this way from the board back to the cabinet, and we're moving that way. No current in this wire, because we have to move it perpendicular. So Omar, how are we going to have to move this in order to make current, right?
No?
Oh, I see what you're saying, right? Why don't you go back that way? Go ahead, right?
This way, right?
Yeah, you can go that way. Yeah. No, sorry. Where do you want me to go? Sorry. Okay.
What are you doing?
No, you choose.
No, where do you want me to go?
Doesn't it go this way? Yeah, so you go that way or something. We just did
Go
this
this
way.
way. All right. So you want me to go here,
Yeah.
right? And how you want me to move? No, you tell me.
Which way is this?
You tell me. If I have to move this
This way.
perpendicular to the field, right? If I go this way,
Which-
right? Or this way, right? The field is running from front to back, but Omar and I are moving this conductor side to side. As we would move this way, right? And as we would move this way, we would see that charges start flowing through this conductor, and we create current. But only if we move it in a certain direction. Okay? Yeah. Thank you for your help. And actually, I mean, that was good. You got to actually had to like figure out where we were going to go and how we were going to move it. And so it was good. Despite the difficulties of dealing with that situation. Yeah.
Is that the situation?
Okay. It's actually not him, it's what he was doing.
Yeah.
So.
Either way.
All right. It's by moving this conductor perpendicular. That is the only way that the charges experience a force. Charges don't move on their own. They have to be made to do so. In the last section, when we talked about current from a voltage source, those charges move from an area of high energy to an area of low energy, right? High electrical potential to low electrical potential. That's what caused them to move. But in the case of this conductor, right, that we're talking about here, there is no voltage source. So something else has to get them to move. It's the magnetic field. But the magnetic field only causes it to move if we move it in a certain way, specifically perpendicular. Okay? All right. That movement perpendicular to the field causes us to generate electricity in a way that maybe isn't as straightforward as the current we talked about earlier. We use this idea to generate something that we call alternating current. Okay? First, sorry. Now this recording isn't going the way it's supposed to, but let's go here and let's go here. Yeah, there we go. All right. Up on the board is a picture of an AC generator. Okay? They're just moving equipment somewhere. They have to go play some music somewhere. Live in nursing home, if I remember correctly. Up on the board is a picture of an AC generator. An AC generator looks a lot like the electric motor that we introduced in yesterday's lecture. It's just a loop of wire, and it has some magnets. And before we ran a current through, in the motor, we run a current through that wire, like we attach it to a battery and run a current, and that current causes it to electric field, and that causes it to spin. Okay? But here, there is no voltage source that's connected to it. Right? It's just magnets and this loop of wire. But we can still get it to spin if we like spin it with our finger or whatever it might be. As it spins through this magnet field, current is generated in that conductor even though it's not hooked up to a battery because of the way that the loop moves within the field. Okay? So, if we look at it at some specific times, okay? When that loop of wire, in this case it's a square, but it could be a circle too, when it is flat in between the two magnets, we are going to induce a current in that situation because the loop is moving perpendicular to the field when the loop is flat. But if this loop continues to spin, eventually it ends up looking like this. Does that make sense? You guys have a picture of this, by the way, on the left-hand side of your outline right there. Okay. Here, the way that it's moving now, it's spinning, right? But if we look at this part and this part, like the top and the bottom, in this case here, it's moving parallel to that field. So it doesn't produce any current. If we look at it a quarter turn later, it's flat again, but the two sides of this loop, notice this side here that's outlined in red, okay? If we go back 2 pictures ago, the red side was over opposite of where it is now. Does that make sense? You can see the red side of this loop right here, okay? If we go half a turn later, now the red side is over here. Again, it's moving perpendicular, but now it's moving up, whereas in the last picture it was moving down. Does that make sense? Kind of, sort of, maybe? You don't have to understand it perfectly, but Christine, you just gave me that face, so I'm gonna because you're not the only one, I'm sure, right? But if we, Christine, if I do this, okay? Like I said, I know you're not the only one. Here, let's do this. If I do this, okay, one side of that magnet is north and one side of that magnet is south, okay? When it's spinning this way, north is coming towards all of you guys, right? But when it goes back around this way, now north is going away from all of you guys. And then when it comes back around again, north is coming towards all of you guys. And then when it spins around again, north is going away from all of you guys. Does that make sense? Okay. So as this thing spins, yes, one side of the magnet is always coming towards you and the other side of the magnet is always going away from you, but it flips which side's coming towards and which side's coming away, right? North, south, north, south, north, south. That's the same thing with this loop of wire. As it spins around, one side is going up and the other side is going down, but it keeps flipping which side is going up and which side is going down because it's going in a circle. What that does is that it keeps creating current. Let me blow this picture up here so you can see it a little easier. It keeps creating current, but based on which side of the loop is going up and which side of the loop is going down, sometimes you'll see, like in the middle section or here in the second picture, and you guys have this picture, you guys have this chart on your outline. Sometimes that current is in a positive direction because it's above the x-axis, right? But sometimes that current is in a negative direction. So what's actually happening in there is that the electrons move within that wire, but it keeps changing which direction they move. Sometimes they move clockwise, sometimes they move counterclockwise. Sometimes they move clockwise, sometimes they move counterclockwise. So it is current because the charges move, but it's different than the current that we talked about before. Catherine, go ahead.
So is that like what happens when the light bulb flickers?
Kind of, yes. Although not, yes. But let me go a little bit further with that and you'll see why it's not totally what you think it is, okay? We call this alternating currents because the current keeps changing directions at a nice regular interval, depending on which way that coil of wire is spinning. So the fact that we're making current from a circle of wire that keeps flipping back and forth, we are making current, but changing which direction those electrons flow. This is different than the current we talked about earlier in this unit, where we talked about direct current. When we hook up something to a battery, right, those charges always flow from the negative terminal over to the positive terminal. Only one way. But that's not the case here, because we're moving them in a different fashion. We're not moving them based on energy, we're moving them based on the magnetic field. Okay? Good there? This is how we produce electricity in our society. Our power plants produce electricity in this fashion. Over here, you'll see on the side, there is this green thing that's labeled the electric generator. Okay? All an electric generator is a big loop of wire. Usually it's lots of loops of wire. And they spin inside of a big magnet. Now, the key to what kind of a generator it is how do we spin the wire? It won't spin on its own, we have to turn it. So what do we use to turn it? Well, depending on what kind of generator you have. If you have a windmill, right, we hook the wire up to the center part of the windmill, and as the windmill turns, guess what it does to the loop of wire? Turns the loop of wire, right? If you go to like Niagara Falls and see the power plant that's there, what do we use to turn the wire? The water that's flowing over the falls, okay? But if you don't live in a windy place and you don't live by a waterfall, you got to turn the wire somehow. Most power plants work on steam power, right? We heat up some water really, really hot and turn it into steam. And then we let the steam out of a little pipe and shoot it at the generator. And as the steam comes out, it hits the loop of wire, and guess what it does to the loop of wire? Spins it around in a circle. How you make the water hot determines what kind of power plant you have. The power plant that we get our electricity from here over in Avon Lake, which is closing sometime soon, but right, is a coal power plant, right? They heat up the water really hot by burning coal. And that heats the water up until it boils and it turns into steam. Okay? This picture here is actually a nuclear power plant. Okay? A nuclear power plant uses a nuclear reaction to heat up the water. But it still turns the water into steam, and we still shoot the steam at the generator and turn the wire and cause the electricity. Okay? It all works the same way, it's just a matter of how do we turn the wire. Okay? So, an AC generator uses mechanical energy of some kind, whether it's water going over a waterfall, or wind, or steam. It uses some kind of mechanical energy to turn a giant coil of wire inside a big magnet. As that wire turns inside the magnets, we keep getting current, alternating current. Okay? Good there. You okay with at least the general operation? We'll talk way more about this power plant now that you know a little bit about how electricity is generated, and we'll talk about how it works. Easy, everybody. We got like 8 minutes left because we're on homeroom schedule today. All right? And we're not done yet.
So tell us when we have 5.
Well, do the math, Maura. Do the math, all right?
But what time does it end since you said 3?
Well, I said we have 8 minutes left, and what time is it now? So, all right. So, in order to wrap this unit up, back in the 1860s, a guy named James Clerk Maxwell publishes a paper where he puts forth a couple of equations. these equations are not like y equals mx plus b. There's like calculus and funny symbols and all kinds of things. But these equations he uses to represent how light works. How does light travel from this light bulb to your eyes? Or how does it travel from the sun to here? And we refer to them as Maxwell's equations. Okay? But the important thing that he throws out there is the idea that this concept that we call light and a lot of other things that we'll talk about later on are totally based on the relationship between electricity and magnetism. Over the past couple of days, hopefully you've seen that these ideas of electricity and magnetism are linked. You can't have one without the other. That one will cause the other and vice versa. They are two concepts that are together that can't be separated from one another, right? This idea that electricity and magnetism are linked to one another, one causes the other and vice versa, is how we can transmit energy long distances without losing it to things like resistance and wires and things like that. Okay? We will spend a large amount of time later on in the year talking about electromagnetic waves. Just know that your electromagnetic waves are the way that your eyes see, the way that we send radio signals, X-rays, all kinds of applications that we use in the real world depend on that relationship between electricity and magnetism. They are linked together, they are one and the same, they depend on one another. You can't separate one from the other. Okay? Good idea? All right. So, we have finished up all the things that we need now for this unit. We've covered all the things on the objective sheet, right? The magnetism stuff towards the end, all right? Maybe not quite as much as the electricity stuff early on. You might not see as much of that stuff on the test. But you have two quizzes that I've given you so far for this unit. One was on just like what is charge and methods of charging and stuff like that. The second one was on voltage, current, resistance, and circuits. Okay, so take a look at those. You've got several outlines. The one lab, the series and parallel circuits lab that I gave back to you today, right? So those are the resources that you have. Tomorrow, come with questions. I will also have some demos ready for you guys so we can see some of these things in action. Okay?